Hello. Today we're going to be solving systems of equations, but these equations are going to have three variables. So a system of equations, the solution works because it works in all of those different equations. So visually we're used to seeing just two lines and the intersection of those two lines being the solution that works in both of those equations. When we go to three variables, we're going to be looking at planes. So we're extending from the second dimension to the third dimension. So we're looking for where three planes intersect. And so there can be a couple of cases here. The first case is that you can have a solution, meaning there's exactly one point that all three of those planes have in common. A good example of that is if you look at the very corner of any room, that corner is in all three planes. And so we would be able to find that solution. Now, what we're going to do algebraically, we're used to seeing it as x comma y, but that's only in two dimensions. So to extend to that third dimension, we're going to normally write it as x comma y comma z, or if you don't have x, y, and z, you're going to go in alphabetical order. Okay, so if you have like A, B, and C, write it in that order. Another option is that you have infinitely many solutions. Now in two variables, normally if you have infinitely many solutions, that means you graph one line, and the next one you would graph the exact same line, and so every point on that line is a solution. In three dimensions, infinitely many solutions is going to be either one solid line. An example of that, it's a little bit stretched out, but if you imagine like the binding in a book, that binding would be representative of that entire line that contains, that's part of all of those different planes, the planes being the pages in the book. So infinitely many solutions would have, like I said, either one solid line, and that line is contained in all three planes, or if you had the exact same plane three different times, that entire plane would be, any point on that plane would satisfy all three equations. So that would be kind of that infinitely many solutions, what it would look like. No solutions can actually happen many ways. It's basically all three planes don't intersect at the same spot. So no solution, here's two examples of that. The first one is any parallel planes, they're never going to intersect. So that would give you no solutions. Now you might have planes intersecting, but they might not all intersect at the exact same point or points. So therefore that also would yield no solution. So let's take a look at actually solving these and trying to get these solutions. So as you can see, we have three different equations because we have three unknowns. So what I'm going to do is I'm going to keep on using elimination until I can whittle down my answers to only have an x and then or y or z, and then after I know one of them, I can find another and yet the third. So here's the process and how to do it. What I'm going to do is I'm going to label my three equations A, B, and C. And I'm purely doing this just so you can follow work really easily. I'm going to pick a variable to eliminate. And so looking at this, to me, it looks like I want to eliminate y just because I have that lone y in that B equation. So I'm going to go ahead and be very clear about this. I'm going to eliminate y. So I'm going to pick equation A and equation B to do this. For equation A, I don't have to multiply by anything, so it's 3x minus 2y plus 4z equals 35. For equation B, in order to eliminate y, I have to take b and multiply it by 2. So I'm showing my work here doing 2b. So I would get negative 8x plus 2y minus 10z equals negative 72. So when I combine these together, I get negative 5x minus 6z equals negative 37. Now looking at that, I can see, wait a second, I don't have enough information to actually get an answer yet. So I'm going to pick the exact same variable and I'm going to eliminate it again. So eliminate y once more. But the problem is I already picked A and B, so I can't pick that combination again. So what I'm going to do is I'm going to pick B and C personally. So looking at this, I need to take B and I need to multiply it by 3. So that's going to give me negative 12x plus 3y minus 15z equals negative 108. For c, I don't have to multiply by anything, so I just write it down. And then when I combine, I get negative 7x minus 12z equals negative 77. So pick one variable and eliminate it twice. Because now what I have done is I have now two equations. I have this one, and based off of those, that's a system that I'm used to solving. So looking at those two equations, I'm going to go ahead and eliminate z from this one. So I'm going to take this first equation and I'm going to multiply by a negative 2. So I'm going to get a 10x plus 12z equals positive 74. So my z's are eliminated. I get 3x equals negative 3. So therefore x equals negative 1. So now my answer, as I'm looking at this, it's supposed to be x comma y comma z. So for this one, I notice that I have my x value. I can go ahead and plop that in the x spot. I need to find my y and my z. Now, good news, you don't have to redo this whole process. Once you know x, all you have to do is go back one level and plug x in, and then you can solve for another variable. So we're going to do negative 5 times negative 1 minus 6z equals negative 37. And so negative 5 times negative 1 becomes positive 5, and I subtract it over to the other side, and I get negative 42. So therefore z equals 7. So now in my coordinate point here, I know x and I know z. And so since I now know 2, I have to go back yet one more layer here to solve for the missing one. So you can basically take A, B, or C, pick up whichever one looks the nicest to you. I'm going to pick A. I'm going to plug in the ones I know. So I know x is negative 1. Oops, sorry, that's a minus sign. Minus 2y plus 4z, but I know z is 7 equals 35. And so now this is enough information to get y by itself. I get negative 2y plus 25 equals 35. So I get y equals negative 5. So with systems of equations, even though it's three variables, just like two variables, you can go ahead and check your answer. You can take A, B, and C, and if you plug in x, y, and z into each of those, you should get the totals that you see on the right-hand side of those equations. So checking your answers for this one can help you figure out if you actually have the correct answers or not. So let's go ahead and try another one. So sometimes when we're using systems of three variables, weird things would happen. So looking at this, I'm going to go ahead and label this A, B, and C. I'm going to pick a variable to eliminate, and to me right now, Z is looking kind of nice if I go ahead and eliminate Z. So I'm going to pick A and C because I don't have to do anything to either equation to get Z by itself. So if I just go ahead and write those out and combine them, my z's are eliminated. I get 5x minus 3y equals 22. And so I'm going to pick the exact same variable and do it again. I'm going to eliminate z. So I'm going to go ahead and go with a and b. So for my a equation to eliminate z, I'm going to have to multiply by negative 2. So I'm going to get negative 4x plus 8y plus 2z equals negative 20. And for the other one, I just write down the exact same thing because I don't have to change it. But here's where something weird happens. As I'm eliminating it, all of my variables cancel out, and I get 0 equals negative 4. So if at some point in your solving, your variables get eliminated, you ask yourself, is this true? This one is not true, and so it's going to be no solution. If you get a true statement, that would be infinitely many solutions, and we'll talk about that tomorrow with the 3.5 day 2. So let's take a look at one more example. Now we're going to go ahead and have to define our variables. Looking at this, I don't know the number of balls, the number of bats, or the number of bases. But I do know that 10 were sold, 10 balls, 3 bats, and 2 bases were sold for a total of $99. The next one would be 4x, 8y, and 2z equals 78. And the last one, 2x, 3y, and 1z equals 3360. So now what I can do is label this A, B, and C. And you can pick whatever variable you want to eliminate. I'm going to go ahead and eliminate z because I see a solitary z over there. So I'm going to go ahead and do A and B. But for B, I'm going to multiply by a -1. So I'm going to rewrite A, and then I'm going to take each value in B and multiply by -1. When I combine those, then I get 6x minus 5y equals 21. I'm going to eliminate the exact same variable once again. And for this one, I'm going to pick A and C, but I have to multiply C by -2. Which gives me -4x minus 6y minus 2z equals -67.2. So I combine those and I get 6x minus 3y equals 31.8. So almost there. So I have 2 different times I eliminated z. I'm going to take my answers, both of these resulting equations, and now I'm going to do elimination again. We kind of lucked out because the x's are the same number, but I just have to make one negative. So I make everything in that equation negative, and I get 2y equals 10.8. So therefore y equals 5.4. So then you can pick either equation to go back now one level. So if y equals 5.4, I can plug that back in. So we get 6x minus 27 equals 21. 6x has to be 48, so then x has to be 8. And so now I go back and I've found x and y. So I'm going to zoom out so we can see. You can pick any equation you want to, and you can go ahead and plug in x and y in order to find z. So looking at this one, I think c looks the nicest to me. I'm going to go for c. So I'm going to do 2 times 8 plus 3 times 5.4 plus z equals 33.60. So I get 32.2 plus z is 33.60. So therefore z would equal 1.4. So one ball is $8, one bat is $5.4, or $5.40, and one base is $1.40. So what we would do then is if we wanted to go back and answer this specific question, all of those together, you'd have 8 plus 540 plus 140, and so all of those together would equal $14.80 for one of each. So thank you very much for listening.